Okay, so we are going to start the sixth section of the fifth chapter, Real Exponentiation Part 1. We have already seen exponentiation where we defined this. Let us start and see what the author has to say in the beginning itself. In section 4.3, we defined exponentiation x to the power n, where x is a rational number and n is a natural number, or where x is a non-zero rational number and n is an integer. We have already seen this. Of course, exponentiation doesn't mean this symbol. This symbol is a power of x, the nth power of x. Exponentiation is the process of exponentiating a rational number or whatever it is to a specified power. Now, what we want to do is that we want to do the same thing when x is a real number. So that's where the first definition of this section comes. Definition 561, it has a name also. Exponentiation of a real number by a natural number. Just like what we did in the case where x was rational, here also there will be two definitions. First, we are going to define x to the power n, where x is any real number and n is a natural number, and then we are going to define that same x to the power n, where x is a non-zero real number and n is any integer. There also we needed the non-zeroness of x to define x to the power n properly when n is a negative integer. Here also the pattern will be the same. So let us see the definition. The definition will also be exactly like what we previously had for rational x. Let x be a real number. To raise x to the power 0 or x to the 0th power, we define equal to 1, just like before. Now, suppose this is in the beginning when our exponent is a natural number, then the definition naturally is recursive. Now suppose recursively that we have defined x to the power n for some natural number n. Then define the next one, x to the power n plus 1, to be this product of x to the power n and x. So you can see that it's exactly like the one we had before when x was a rational number. Naturally, there is a next definition, a follow-up one. Exponentiation of a real number by an integer. Okay, so here x has to be, the base has to be non-zero to allow for any integer exponent. Let x be a non-zero real number. If our exponent n is a natural number, I mean it's going to be an integer now, but if in particular it's a natural number, then we don't need to define anything new. Already we know what x to the power n means by the previous definition. So we only need to define the case where n is a negative integer, and that's what we are going to do. For a negative integer n, we define x to the power n equal to the reciprocal of x to the power minus n. Now there are a few things to be said here about this definition. The one thing is that the author uses minus n. For tau, minus n is a negative integer, means n is a positive integer. We are, however, using n, but clearly there is no difference, because for him he writes minus n here, and in place of minus n he writes n. It looks more natural than this. However, we decide to use n because we are defining this symbol, and we are considering the cases separately where n is a natural number and where n is a negative integer. So that's why we are using n here. But clearly the two definitions are equivalent. It's just a matter of writing n or writing minus n. Okay, now the next thing is, what have we done here? Let us see. X is a given non-zero real number. Okay. One can prove by induction and using properties of real numbers that we have proved already, that for this such an x to the power m is also non-zero for all natural numbers m. This can be proved quite easily using induction on n. Fine. Now our n is a negative integer. That means minus n is a positive integer. So for that special value of m, that is minus n, also we will have this. It's a non-zero real number. So its reciprocal exists, is a real number. and that is equal to x to the power n. That's what x to the power n means by this definition. So there is no problem with this definition, and it makes sense. Okay, so we now have the meaning of x to the power n, where either x is any real number and n is a natural number, or when x is any non-zero real number and n is any integer. Now recall that when we defined x to the power n, where x was rational in these two cases, after that we stated and proved some properties, rules of exponent, inequalities involving exponent, things like this. X to the power n plus m is equal to this, then this. So similar statements or similar lemmas or propositions, whatever they were, are also true for real exponentiation. We are now, let us state that and prove that, but the proof will not be, we will not go through all the details in the proof here. Instead, we will present a meta proof instead of a proof. We will see what that means. So let us first state the results for real exponentiation. Statement also will be very short. We will just simply say that whatever we had there is still true here in this case, where now our base is real, x is real. But even before that, there is a line clearly these definitions are consistent with rational exponentiation. Given earlier. What that means is that if in place of x here, because now x is real, so x in particular can be rational also. If our x is rational, then we get the exact same definitions that we had then. Okay, so that's what means when we say that these definitions are consistent with rational exponentiation. Okay, now comes the next proposition. All the properties in proposition 4.3.10. You can go back to the statement, or you can just simply try to vaguely recall using these rules. It's these things that we had there. Proposition 4.3.10 and proposition 4.3.12. I think if I am remembering correctly, in proposition 4.3.10 we allowed the exponents to only be natural numbers, but in proposition 4.3.12 we allowed the exponents to be integers. So essentially this one contains this one, okay, inside of it. Remain valid if x and y are the bases that we have there in these propositions, are assumed to be real numbers. Instead of just rational numbers. And in place of a proof, we have a meta proof, which is less a proof and more a way of how to write a proof. You will see, okay, let us first write the things and then we will see what this means and why a meta proof itself is enough in this case. If one inspects the proofs of proposition 4310 and proposition 4312, one notices that these proofs only rely on the laws of algebra. That these proofs only rely on the laws of algebra and order. For the rationals. Specifically, proposition 424, which has the laws of algebra, which just simply the author also says collectively all the laws are we express the fact that all the laws are true for the rationals by saying that the rationals form a field. Okay, so that thing, proposition 424 and proposition 429. 429 has the usual laws of order for rational numbers. Okay, so the proofs of these two propositions depended only on the laws of algebra and laws of order for the rational numbers. And now we notice that the exact same laws of algebra and order are also true for real numbers. So whatever we did in these proofs for rational numbers, we can also do for real numbers, because those same laws are also true, and since the proofs depend only on those laws. So that's what we write next. But by proposition 5311, the references should be correct, okay? But by proposition 5311, which we have already proved, and proposition 547, So I think proposition 5311 contains the laws of algebra, which does not immediately say that I don't think it immediately says that the real numbers form a field. It says that the real numbers form a commutative ring. Anyway, whatever it is, so these two propositions contain the fact that the laws of algebra and the laws of order that we already know are true for real numbers, and the identity that, of course, when you multiply any non-zero real number with its reciprocal in any of these two orders, you get 1. We know that these laws of algebra and order continue to hold for real numbers. Thus, we can modify the proofs of proposition 4310 and proposition 4312. In the case when x and y are real. For 312, in the case when x and y are real. As far as writing the actual proof goes for these things, for this proposition, you just repeat the proofs of 4310 and 4312. The only difference is that wherever the bases x and y appear in those proofs, now they are real. Just change the word rational to real, that's it. That just gives you the proofs. So that's why it's the meta proof. It's a proof about the proofs. Okay, now we can turn to the task of defining x to the power n, where n is no longer just an integer but a rational number. This, however, we will do in steps, and the first step towards this direction is the next definition. Let x be a positive real number and n be a positive integer. Okay, we are now going to define the nth root of x. We define x to the power 1 by n, also called the nth root of x by the following formula. The nth root of x is defined to be the supremum of this set, the set of all real numbers y such that y is non-negative and the nth power y to the power n is less than or equal to x. We know from our definition of supremum of a subset of real numbers that any subset of real numbers has a supremum. It's a different matter that sometimes it becomes minus infinity, sometimes it becomes plus infinity. We will now show that for our choice of x and n, this is always going to be a real number. Okay, it will not be minus infinity or plus infinity. Let us recall in this regard that supremum becomes minus infinity when the underlying set is the empty set, and supremum becomes plus infinity when the underlying set is non-empty but has no upper bound in the set of real numbers. Those two cases are not going to appear here. Here we will get a real number. So that is that we will prove in the next lemma, but before that there are some other things. The definition ain't over yet. We often write this symbol for x to the power 1 by 2 and call it the square root of x. You already know these things. Note that we do not define this when x is equal to 0, and we also do not define this when x is less than 0. The former of these two cases or issues, whatever you want to write, you can write, will be addressed soon. And for the latter one, namely when x is negative, we leave x to the power n undefined. For the rest of this text, when x is negative. One can define this when x is negative after one has defined and developed complex numbers. We will do that in section, we will define complex numbers in section 15, chapter 15 in analysis 2. However, we will not define nth root of complex numbers. What I am trying to say, we will not define x to the power 1 by n when x is negative. However, we shall not do so, we refrain from doing so. Okay. Now, simply saying that this is the supremum of this set is not very useful. If it is not a real number, if it is minus infinity or plus infinity, then we can't do anything much with it. But we will now show that it's always a real number. And that is the next lemma. 5, 6, 5. Existence of nth roots. The lemma is simply this: let x be a positive real number and n be a positive integer. Then the set of all real numbers that are non-negative and whose nth powers are less than or equal to x is non-empty and is bounded above. That means it has an upper bound which is a real number, and this just simply tells us that the nth root that we have defined, which is equal to the supremum of this set, is going to be a real number. So in particular, the nth root of x is a real number. So let us now prove this. The proof will be divided into two parts. The part where we show that this set has an upper bound, that will be divided into two parts based on whether x is less than or equal to 1 or greater than 1. But we can show very easily that this set is non-empty. Oh, I think I forgot to, this set has been given a name also. It's called E. E is defined to be equal to this set. Note that since x is positive, we have 0 to the power n, which is equal to 0, that is less than or equal to x. It's actually strictly less than x, but that also means it's less than or equal to x. Hence 0 belongs to E, so that E is non-empty. Zero is a non-zero real number. What the hell am I saying? 0 is a non-negative real number whose nth power is less than or equal to x. So it belongs to E, and that is why E is non-empty. We now show that E is bounded above. Okay, two cases arise. First, we assume that x is less than or equal to 1. Suppose there exists an element y in E such that y is greater than 1. Okay, so suppose that there is an element y in E such that y is greater than 1. Then y to the power n is also greater than 1. The author asks why. So you have to actually somehow prove using induction on n, although n is fixed here, but as a statement about inequalities, you prove by induction on n that whenever y is a real number greater than 1, y to the power n also has to be greater than 1. It's very easy. Okay, it just uses elementary properties of order for real numbers. Then y to the power n is greater than 1, and hence y to the power n is greater than x, because x is less than or equal to 1. And this is a contradiction. It's a contradiction because since y belongs to E, so y to the power n has to be less than or equal to x, not greater than x. So that's the contradiction. So our supposition is wrong, that is we must have, that means what? No element in y can be greater than 1. All the elements in y have to be, that's why, less than or equal to 1. For all y belonging to E. All the elements in E, sorry, I think I said y. All the elements y in E have to be less than or equal to 1. Thus, in this case, 1 is an upper bound for E. Then we next look at the other case where x is greater than 1. Next, assume that x is greater than 1. In this case, just like in the previous case we showed that 1 is an upper bound, in this case we aim to show that x is an upper bound. So we, contrary to that, we suppose the existence of an element in E which exceeds x. Suppose there exists an element y prime in E such that y prime is greater than x. Then, since x is greater than 1, we have y prime also greater than 1. Now combining this and this, one can again just like before prove by induction on n that y prime to the power n is going to also be greater than x. Y prime, sorry. These parts which we are just simply saying and not proving in detail, they are left to you because they are quite easy. This is greater than x, again a contradiction. Because y prime being in E should have its nth power less than or equal to x, not greater than x. So our last supposition or second supposition is wrong. That is, we must have y less than or equal to, or y prime less than or equal to x for all y prime belonging to E. So in this case, x is an upper bound for E. So whatever the case is, our set E is bounded above. That's what we wanted to show. It's a non-empty set that is bounded above, so its supremum is a real number, which according to our definition is the nth root of x. Okay, now next we state some properties of this supremum. What sort of properties does it have? What sort of algebraic properties does the supremum have? The first one, of course, is what we expect. When we take the nth power of the nth root, we actually get x. Okay, so let us state all the things in the form of this next lemma. Lemma speaks. Let x comma y be positive real numbers and n comma m be positive integers. Okay, then the following are true. Part A, if y is the nth root of x, then the nth power of y is x. That's what we expect of the nth root of x, and that's what happens. Conversely, if y to the power n is equal to x, then y has to be equal to x to the power 1 by n. Note, keep in mind that x and y continue to be positive real numbers, okay, not just any real numbers. If this is true, then y has to be equal to this. So these two things say something about the nth root. First of all, the nth power of the nth root equals the original number, and if the nth power of some positive number equals the original number, then that positive number must be the nth root. It cannot be something else. So this part B tells us that the nth root of a number, in the sense that if, say, instead of defining the nth root using supremum, one just simply says that the nth root is defined by an equation like this, which we normally do. We say that the square root of a positive real number is a real number whose square is that given real number. Using this equation, if one defines the nth root, then it turns out that such a number first of all exists, and there is only one nth root. There is no two values of y. So that uniqueness aspect comes here in part B. Then in part C, this is also important. X to the power 1 by n is a positive real number. Then in part D, we deal with some inequalities. We have x greater than y if and only if the nth root of x is also greater than the nth root of y. Then part E, let k be a positive integer. If x is a real number that is greater than 1, then the kth root of x to the power 1 by k, if we keep on changing k, if we change k, then x to the power 1 by k becomes a function of k. So as a function of k, this is decreasing. The higher the value of k, the lower the value of x to the power 1 by k will be. So the square root of x will be greater than its cube root, which will be greater than its fourth root, and so on. Okay, so then this is a decreasing function of k. X remains fixed. Okay, x does not change, k changes. If x is less than 1, then x to the power 1 by k is an increasing function of k. So say if x is 1 divided by 2, then for 1 divided by 2, its square root is less than its cube root, which is less than its fourth root. So here the exact opposite thing is will happen. In the other case, the only one left is this: if x is equal to 1, then x to the power 1 by k is also equal to 1. Then there is a part f. We have xy all to the power 1 by n. Nth root of xy is the product of their nth roots. And finally, in part g, we are taking nth root as well as mth root, one after another. This is the same as the nth root of x. And the proof of this we will do in that is the first exercise at the end of this section. So there itself we will prove it when we solve the exercises. Now there are some words after this. You may note that this definition might possibly be inconsistent with the definition of x to the power n, with our previous notion of x to the power n in this particular case, in the case when n is 1. One root of a positive real number and the 1th power, are they the same thing? when n is equal to 1. Fortunately they are, but it is easy to check that the 1th root of x is x, which of course by definition is also equal to the 1th power of x. So there is no inconsistency. This part of course comes from the definition of exponentiation that we have seen in this video. What about this part? The fact that this becomes x itself, it has to be proved. It does not come from here anywhere. Just one thing, I leave this to you, of course. Just see what it is. According to our definition, it is the supremum of all real numbers which are non-negative and such that the first power of y is less than or equal to x. So to show that this is equal to x, you have to prove that the supremum of this particular set is actually equal to x. That will tell you that this is equal to x. So this part you have to make sure that this is true, or you have to prove this part. It's not something very big. You just have to convince yourself that in this case x is the supremum. So actually there is no problem with x to the power 1 by n and x to the power n when n is 1. They give us the same value x. So there is no inconsistency. One more thing. One consequence of part B of this lemma (566b) is the following cancellation law, which is very useful. If x and y are positive real numbers and n is a positive, is it positive or it's just an integer? No, because in this lemma we have positive integers. And n is a positive integer, then this equation implies x equal to y. So it's cancellation of the exponent n. How exactly does it follow from this lemma 566 part B? Let us see in part B what is it that we have. So for us x and y are positive, just like what the lemma says, n is also a positive integer. Fine. So this means what? This equation means this thing. This is a real number. This is some real number. So by part B, since but before we do these things, we need to show one more thing. Since x is positive, x to the power n is also positive for every natural number n. In fact, every positive integer n, and this fact can be proved by induction on n very easily. You can almost see that. So the r we have here is actually a positive real number, and x and y are given to be positive. So by part B of this lemma, x is going to be the nth root of r, and also by part B of this lemma, y is also going to be the nth root of r. So that's why they are equal. Okay, and that's how we get the cancellation law. Note that this cancellation law only works when x and y are positive. Because if that is not true, then the cancellation law is not true. We may not be able to cancel the exponent from both sides. We have, which is demonstrated by this example, minus 3 whole square is equal to 3 square, where you can think of minus 3 as x and 3 as y. So they are not both positive, and you cannot cancel 2 from both sides. But minus 3 is not equal to 3. Okay, so the cancellation law fails here because the bases are not both positive. Okay, now we come to having defined the nth root and having, I can't say proved, but having stated these basic laws that nth roots must follow, we are now in a position to define exponentiation, where the exponent is a rational number in this very nice way using nth roots. So that is the next definition, 5, 6, 7. Let x be a positive real number. Let q be a rational number. Any rational number, but x is a positive real number. To define, our aim is to define x to the power q, whatever that is going to be. We write q as a quotient of two integers, because that's what rationals are. We have already seen these things in detail. Although in our construction of rational numbers, the quotients first of all were formal quotients, but later we showed that they are in fact equivalent to actual quotients after defining division of rational numbers. But for any rational number, we still have this. It is a quotient of two integers. For or we write q equal to a by b, where a is an integer and b is a positive integer. This we can always do. Now we define x to the power q to be the eighth power of the bth root of x. The bth root of x is this, and the eighth power of that is this. Note that since x is a positive real number, its bth root first of all exists. We have already shown that in the existence of nth roots, and that is because b is a positive integer, so the bth root exists, and its eighth power of course can be taken in the usual way. A now is any integer, so things are one more thing is there. Note very carefully that in lemma 566 part C, from there we get this additional fact that x to the power 1 by b, the bth root of x is a positive real number. In particular, it's not 0. So even when our integer a is negative, there is no problem forming this power, this eighth power of x to the power 1 by b, because now our x to the power 1 by b is a non-zero real number. So even when a is negative, we can form the power. So there is no problem with this definition. No problem means at least with the symbols we don't have problem, but there may be another problem. We are coming to that now. The other problem is this. Let us take a specific value of x. Say x equal to, for simplicity let us take x equal to 2, okay, and let our rational number be this. Say okay, to make it non-trivial, let us take 8 divided by 9. So that's a rational number. So according to this definition, if we form the power x to the power q, then we should have that equal to this. We have taken a specific value of x, so the 8th power of the 9th root of 2. But the problem is that besides being 8 divided by 9, the rational number is also many other things divided by other things. For example, it is equal to this. So again, by that same definition, we should also have this. X to the power q should also be the 16th power of the 18th root of 2. If we look at these numbers and think of how one can calculate these things, for example, if one actually writes this thing using the definition of the 9th root, it is going to be this. No. Y to the power 9 is less than or equal to 2. And if one calculates the 18th root of 2, these are very different sets. Naturally, the suprema will also be different, likely. Now, if one calculates the 16th power of this supremum, and on the other hand, if one calculates the 8th power of this supremum, can you really see that they are equal? I cannot see. Immediately, it is very difficult to say that these two things have to be the same real number. If they are not, then there is a problem with this definition, because then the answer will depend entirely on our choice for how we are representing the rational exponent. You can have infinitely many different types of representations for q as a quotient of integers. If every time we are getting a different answer, then that is not a very good definition. We won't have a single value for x to the power q. We will have a set of values which then may not be of much use. Fortunately and surprisingly, these two things turn out to be equal, and not just these two things. The actual value of x to the power q does not at all depend on what a and b themselves are. Ultimately, the value turns out to be equal, and that is our next result, next lemma. Okay, we are going to prove that. Now, before we do that, is there something else? No. Yes, the next lemma is this, which tells us that the definition gives us a unique x to the power q, and hence exponentiation of a positive real number by a rational number is well defined. Okay, so let us see the lemma. Let a prime be integers and b comma b prime be positive integers such that a divided by b is equal to a prime divided by b prime. So these are two different representations for the same rational number. It's like having two different representations for q here. And let x be a positive real number. Then the two ways of calculating that exponent, the 8th power of x to the power 1 by b and the a prime power of x to the power 1 by b prime, they are actually equal. Let us now see the proof. Depending on the sign of a, there are three cases. The following cases arise. A is positive, A is 0 and A is negative. First assume A is positive. Now if we write this equation slightly differently after cross multiplication, then A B prime equal to A prime B implies A prime is also positive. Let us see why. It is given that A is positive. Note that B and B prime were originally positive integers. So A is positive, B prime is positive, so the left hand side is a positive integer. On the right hand side B is positive, so A prime must also be positive. There is no other way. It cannot even be 0, it has to be a positive integer. So that's why A prime is positive. Now write y equal to this root of x, A B prime root of x, and it makes sense also because A B prime is a positive integer, so we can we can determine the corresponding root for x. But since A B prime is equal to A prime B, so this is also equal to this same thing. Now by that lemma 566 part A, we have what happens when we calculate the eighth power. Eighth power of y. Eighth power of y is the b prime root of x. Can we directly conclude this? That's what I am thinking. Eighth power of y is the, I don't think this is an application of only part A. It has other things also. Now I notice. You see, part, yes, we actually have to apply many things. Why is Tao saying that we are using only lemma 566A? Instead, let us write a number of steps. By lemma 566G, y is equal to this. In 566G, recall that we had this x to the power 1 by n is equal to nm. Can we apply it here? Let's see. B prime is a positive integer like n, and a now is also a positive integer like m. So yes, we can apply. So we have this, and just like that we also have this from this representation of y. Now we can apply part A. Now by lemma 566a, we have y to the power a equal to x to the power 1 by b prime, and y to the power a prime is equal to x to the power 1 by b. Oh, sorry, here 1 by a prime. That is because y is an eighth root of something. At the same time, y is also the a prime root of something. So that's why we have these equations by applying part A of lemma 566. Now here is the calculation. X to the power 1 by, let us start with this one, to the power a. Using this equation we get y to the power a prime whole to the power a. Now in place of this we are going to write a prime a. What is the justification? The justification is that just like the rules of exponent are true for rational numbers, they are also true for real numbers. That thing, proposition for which we gave a meta proof, that is the justification. So this is equal to this, but at the same time this can also be written as y to the power a whole to the power a prime. Okay, and note that we don't have to bother, although these things will be positive, but we don't have to bother about non-zero-ness of y, because now our exponents a and a prime are actually natural numbers. They are positive integers, not just natural numbers, positive integers. So the rules of exponent are anyway true, and in place of this we can write x to the power 1 by b prime whole to the power a prime. So that's what we wanted to show. In this case, where a is greater than 0, we have what we want. Okay, next, if a is equal to 0, then again we use this equation, a b prime equal to a prime b implies a prime is also equal to 0. A is equal to 0 means the left hand side is 0. So the right hand side should also be 0. But on the right hand side, b is already a positive integer. So the only possibility is that a prime has to be equal to the 0 integer. In this case, since both a and a prime are 0, so by our ordinary exponentiation, we get this. Both the sides will be equal to 1 because both the exponents are 0. Finally, assume a to be less than 0. Then again this equation a b prime equal to a prime b implies a prime is also less than 0. Same thing. Now the left hand side is negative because a is negative and b prime is positive. On the right hand side b is positive, so to make that also negative, a prime has to be negative. Then minus a is positive and minus a prime is positive, and hence by the first case we have to the power minus a is equal to minus a prime. Then you just have to take reciprocal and use the laws of exponent that is already true for real numbers. Can you take reciprocals? Yes, you can take reciprocals. Why? Because first of all, bth root of a positive real number x is itself positive, it's not 0. Just like that, b prime root is also positive, and their integral powers are also positive. So on both sides we have a positive real number, so the reciprocals are also going to be equal. Now taking reciprocals on both sides and using rules of exponent, I am not writing that here, we get this. This completes the proof. So now our x to the power q is well defined. Thus, this is well defined for every rational number q. For every rational number q. Then comes the remarks about consistency. Note that this new definition is consistent with our old notion of x to the power 1 by n, y that you will answer, and is also consistent with our notion of x to the power n, y. And why are these questions arising in the first place? It's because both 1 by n and n are rational numbers, so you can think of them in terms of x to the power, as x to the power q. Okay, so whatever, however you think of the things, ultimately you get the same result. The question is how exactly. So that I leave to you. And finally, let us state the next lemma where we allow the exponents to be any rational number, unlike only the nth roots. So that is this lemma 5, 6, 9. Let x and y be positive reals any rationals. Then first of all, x to the power q is a positive real. B, the rules of exponent, usual rules of exponent, x to the power q plus r is x to the power q times x to the power r, and the other one, qr. C, x to the power minus q is the reciprocal of x to the power q. D, if q is greater than 0, then x is greater than y if and only if x to the power q is greater than y to the power q. Or E, if x is greater than 1, then x to the power q is greater than x to the power r if and only if q is greater than r. If x is less than 1, then x to the power q is greater than x to the power r if and only if, this time it will get reversed, q is less than r, and its proof is the second exercise. Exercise 5.6.2. And okay, so all these things we have done excuse me, are for defining the rational, or for defining the exponentiation where the exponent is rational, but we still have to go to the case where we can define the meaning of x to the power q where q is a real number and x is a positive real number. But we will defer that until we have developed all the things and the theory of sequences of real numbers. Then only using them we can define such a thing. So we will do that in section 6.7 in a formal manner. And those very general powers of x to the power y where y is a real number also have similar properties like this one. So that we will do in the next chapter actually. So this is the last section of this chapter 5. In chapter 6, in the next video we are going to go to chapter 6. We will develop the theory of sequences of real numbers. So until then, it's me, Lucifer, from a mathematical room. If you want to say something about these things, you can write in the comment section below, or you can also mail me to that usual address here. So until the next time, have a nice night.